Hello everyone, I am Dr. John AROCKIARAJ presenting you a mathematics topic in functional analysis. I am Dr. John AROCKIARAJ, Vice Principal and Head from St.Joseph's College of Arts and Science, Cuddalore, India. For the first one, we will define about the normed linear space. It is nothing but a linear space n in which all the vectors satisfies these three conditions. Norm of x greater than or equal to 0 and norm of x is equal to 0 if and only if x is equal to 0. Norm of x plus y is less than or equal to norm of x plus norm of y, and norm of alpha x is equal to modulus of alpha into norm of x. And we write the norm of x to be in the symbol, and this is regarded as the length of the vector x. And this function can be reported as a metric if we define the metric d to be is equal to norm of x minus y. And afterwards we can say a Banach space is nothing but a complete normed linear space. Now we shall see two simple properties of this particular norm. Xn converges to x implies the norm of xn converges to norm of x. See how. Take the modulus, the difference of the modulus between this, definitely that will be less than or equal to norm of xn minus x. And since xn converges to x, that value is also going to be tending to 0. Therefore, automatically the norm is a continuous function. And also we can go for the jointly continuous. When xn converges to x and yn converges to y, normally xn plus yn also converges to x plus y. See how it is happening. So, so take the difference between the norm, norm of xn plus yn minus norm of x plus y, and that can be written as norm of xn minus x and yn minus y. Individually they become 0. Therefore, automatically xn plus yn minus x plus y within norm tends to 0. Therefore, the jointly continuous is done. Similarly, the next one, when alpha n tends to alpha and xn converges to x, alpha n xn converges to alpha x. Similarly, take the difference between their norms, a norm of the difference between alpha n xn and alpha x, add and subtract one value, similarly alpha n x, and group xn and x together and alpha and alpha, separate it, and you will find in one term norm of xn minus x is there, in another term alpha n minus alpha is there, both of them tends to 0. Therefore, you will get alpha n xn converges to alpha x. Now we shall see a simple theorem on this normed linear space. Now let M be a closed linear subspace of a normed linear space n, and if the norm of the coset x plus m in the quotient space n by m is defined by norm of x plus m is equal to infimum of norm of x plus m with the small m belongs to capital M, then n by m is a normed linear space. Further, if n is a Banach space, then n by m is also a Banach space. How to prove this? The first three conditions just now we stated are to be proved. Automatically norm means greater than or equal to 0 by definition. Therefore, nothing we have problem. Now, if norm of x plus m is equal to 0, what is going to happen? Suppose consider a sequence mk in m such that norm of x plus mk tends to 0, which implies x belongs to m. What does it mean? X plus m is equal to m, and that m is nothing but the 0 element of n by m. So, if norm of x plus m is equal to 0, then x plus m is equal to 0. The first rule is done. And the second one, norm of x plus m plus y plus m can be written as norm of x plus y plus m, and by definition that is equal to infimum of norm of x plus y plus m. Now I can add one more element to m dash, so that x has m and y will have m dash, and these two can be separately written. So one is norm of x plus m and another is y plus m dash. Now you separate this into two different norms, so you will be getting less than or equal to infimum of norm of x plus m plus norm of y plus m dash, and infimum also can be distributed these two terms. So the first infimum will become norm of x plus m and the second infimum will become norm of y plus m. Therefore, the second inequality is true. The third one, norm of alpha into x plus m can be written as infimum of the same, but when we take out alpha from norm, it will become modulus of alpha, which can be still further taken out of the infimum. So by definition that would become modulus of alpha into norm of x plus m. So all the three conditions are true, therefore n by m is a normed linear space. That is the first part of it, and we shall prove the second part of it, that is what we are aiming to be Banach space. Assume n is complete by hypothesis, and we will try to prove that n by m is also a complete space. How to prove this? So take a Cauchy sequence in n by m and take it as xn plus m, and by the property we assume norm of x1 plus m minus x2 plus m to be strictly less than 1 by 2. Similarly, norm of x2 plus m minus x3 plus m is strictly less than 1 by 2 square, and in general norm of xn plus m minus xn plus 1 plus m is strictly less than 1 by 2 power n. And we prove that this sequence is convergent in n by m. How? We'll choose one element from one coset, that is y1 from x1 plus m, y2 from x2 plus m, y3 from x3 plus m, etc. So what will happen? According to the condition, norm of y1 minus y2 is less than 1 by 2. Similarly, norm of y2 minus y3 is less than 1 by 2 square, that is 1 by 2 4. So to 2 square. Continuing in this way, we will get norm of yn minus yn plus 1 is less than 1 by 2 power n. Suppose we take, there is an index m which is strictly less than n, we can write that as m, m plus 1, etc. up to n. Therefore, we find the difference norm of ym minus yn is equal to norm of ym minus ym plus 1, and we are adding and subtracting the same value, so it is not altered, and you separate it next day individually, so that you will get norm of ym minus ym plus 1, in the next term norm of ym plus 1 minus ym plus 2, etc. You will get at last yn minus 1 minus yn within norm, and each of the terms are strictly less than 1 by 2 power m plus 1 by 2 power m plus 1, etc. up to 1 by 2 power n minus 1. By the binomial expansion, if you take 1 by 2 power m, you will get 1 plus 1 by 2 plus etc. That is nothing but 1 minus 1 by 2 power minus 1. So you will get the entire expression will become 1 by 2 power m minus 1. Now, already we have assumed that n is a complete space, Banach space. Therefore, yn will become a Cauchy space, converges to itself. So we take any vector y in n such that yn converges to y. Now if we take norm of xn plus m minus y plus m, it's nothing but less than or equal to norm of yn minus y, which is nothing but xn plus m converges to y plus m. So since y belongs to n, y plus m belongs to n by m, which is complete. Therefore, in the first phase we have proved n by m is a normed linear space. Now we have proved n by m as a complete space. When we combine these two, we will get that n by m is nothing but a complete normed linear space. By definition, that becomes a Banach space. Thank you.